It's an honor to be certainly the first speaker, and pleasure to have one of my students. And I say students only in the sense, and I'm advisor. Alex is a student only in the sense that I assume that's how it will appear in the genealogical project. Otherwise, relation advisor-student is not so clear in this situation. At any rate, it's a real pleasure, and also to see some of Alex's students here. And the term that always comes to my mind in this kind of situation is the Yiddish term nachas. That's usually a term that's applied to children and grandchildren when they come to your house. And if by chance there's someone here who doesn't know Yiddish, then I like to translate nachas as a kind of pleasure that you don't have to feel guilty about. At any rate, the comparison between a father and child, father and son relationship, and teacher and student relationship is something it's quite interesting to see that these two relations are considered quite parallel in Jewish tradition. For example, there's a saying in the Talmud that a person may be envious of someone else's success, but a father is never envious of his son's success, nor is a teacher envious of his student's success. Another less-known place where the two are compared is in the laws of respect. A child should respect his parents, and a student should respect his teacher. And when you look it up in the sources of law, codes of law, you see that they bring the laws of the child respecting the father, and when it comes to a student respecting his teacher, it just says, look up the laws for the child respecting the parent. It's the same. It's exactly the same level. And but there is a difference. One difference is that the student and teacher, whereas in both situations the younger one benefits from the older one, but as far as student-teacher relation, this teacher also benefits from the students. And this also appears in the Talmud, where there's a saying of Rabbi Hanina, that a well-known saying that I've learned much from my teachers, even more from my colleagues, and most of all from my students. The idea is that the student sometimes challenges the teacher, asks him questions, which forces him to think more clearly about what he's teaching. But sometimes it can take, I think in this situation, I think for all of my students, it's true that just to learn mathematics from the student is, I've had that benefit. And but I was interested in looking at and checking out this statement, and I found that the statement appears in an interesting context. The Talmud at one point asks, why is it that the scriptures, the Torah, which represents basically all of Jewish learning, why is it that it's compared to a tree, Eitz Chayim? It's compared to a tree. What is the connection between wood and learning scriptures, learning Torah? And the answer is that with wood, in both cases, as in with wood, a small piece of wood, like a match, can light up you can burn down a forest with a small match. And similarly, let's say the junior student has something to give to the older student, and the proof of this was Rabbi Hanina saying that I've learned most from my students. But I like that particular comparison, because I think that if we think about Alex, that in addition to his written work, which is cold mathematics, there's also certain spirit, certain personality which enters the work. If somebody has heard Alex lecture, you see that there's enthusiasm, and interestingly the word the Hebrew for enthusiasm, hitlahavut, has within it the word for flame, lahava, and just like a piece of wood can ignite other wood, the enthusiasm, a little bit of enthusiasm, can also ignite enthusiasm among the listeners, and I think that that's something that the encouragement, the love for and passion for the beauty of mathematics is something which I think his students and also his colleagues and also his teachers have benefited from Alex. Anyway, I apologize for saying my few words about Alex. I didn't realize it was supposed to be later on, but at any rate, I'll get now down to the subject of the talk, which is Ramsey theory for non-amenable groups. So, what is Ramsey theory? And it's best defined by or described by examples in connection with groups. Ramsey theory really originates with graph theory, but in terms of groups, I mean, the idea in general is that when you have a large structure and you take a large portion of that structure, then there's certain kinds of patterns that necessarily appear in that smaller structure, which is, in some sense, relatively large, which we have to define. What does that mean? In the case of the first theorem of this type was a theorem of a lemma of Schur, Isai Schur, that if you take the integers or the real numbers and is partitioned into some finite number of sets, C1, C2 up to CR. I use C because combinatorialists like to refer to this as colors. If you color the integers with finitely many colors, then one of them for some j, there exists x, y, and x plus y belonging to Cj. Actually, he was interested in proving Fermat's last theorem, and by showing that not only don't you have an equality, but you can't even have a congruence for arbitrarily large primes, and he disproved this. And this lemma shows that you're not going to get anywhere with this approach. Now, Schur himself suggested another result, which became Barton's theorem, that again, if n equals C1, etc., CR, some Cj contains arbitrarily long arithmetic progressions. Now this theorem, which is not trivial but not that hard to prove, was strengthened very much by a summarity based on a conjecture of Erdős and Turan. So we'll start Erdős and Turan here, that if a single set E is contained in n, or the integers, let's start with all the integers, let me write positive upper density, which I'll define in a minute, then E contains arbitrarily long arithmetic progressions. And this is stronger because it's easy to see that if n is divided, or z is divided into finitely many sets, then one of them has to have positive upper density. What does positive upper density mean? It means the following. E has, I'll write it this way, E belongs to positive upper density, PUD, if there exists some positive number, density, referring to density, and arbitrarily long intervals, say I, n equals some number an plus 1 up till an plus k, where k can be arbitrarily long. I should call this ik, with the density of the set, the number of elements in the set that are inside ik in this long interval divided by the length of the interval, which is k, larger than delta. So if you have arbitrarily long intervals with a certain percentage of the set inside that interval, then we say that the set has positive upper density, and then the theorem is that that's a sufficient condition for getting arbitrarily long arithmetic progressions. So this is one of the issues that one can ask for an arbitrary group. Suppose we have an infinite group, some type, and what would be the appropriate, what's the notion of positive upper density which would guarantee a result of this type? Now we'll give something later on. I'll say exactly what that would be, or give some example of what that would be, say for a free group on finitely many generators, and there it's almost what you would think it is. In fact, you can say if you have a, well actually not, if you look at if there's a delta such that all words of this, if you look at the set of all words of a fixed length, then there's a proportion delta of them in the set, and that's for lengths that go up to infinity. Maybe I'll say that later on. But at any rate, this is a theorem which in fact can be extended, and the first extension of it, which is actually quite recent, is to amenable groups. That turns out to be a natural kind of extension, and let me explain why. The reason why, because one way of proving Summer-Rady's theorem, which is called the ergodic theoretic approach, is by the following what you might call a correspondence principle, or at least formulated at least in this situation. First of all, let me write down a theorem. So before I write down the theorem, let me explain what I mean by what's known as a measure-preserving system. So XB mu is a probability space, which means that X is any kind of a space. B is a sigma algebra of subsets of X. For those sets, the measure of those sets is defined between 0 and 1. The measure of the whole space, make it a probability space, will be 1. And the measure is what's called sigma additive, so that if the sets BI are disjoint, BI, BJ disjoint, this implies that the measure of the union of these, and this could be a countable union, is equal to the sum of the measures. Now what about the T? T is a measure-preserving transformation, and this means that a T is a transformation of X to itself, and the measure of the inverse image of any given set, which is measurable, the sets in B are the measurable sets, is the same as the measure of B. So that's a measure, this I refer to as a measure-preserving system. For a measure-preserving system, one has the following theorem. Which is sometimes referred to as the ergodic Summer-Rady theorem. Ergodic Summer-Rady theorem. If XB mu t is a measure-preserving system, and I have a set A, and A is a measurable set with a measure of A positive. It's a non-trivial set, and for any L standing for length, there exists an M with the measure of A intersect T minus MA, intersect T minus 2MA, intersect, T minus, L minus 1, M, A, being non-empty, not only non-empty, having positive measure. Now what's the relationship between, there's sort of an intuitive relationship between the two, because if I think of the integers somehow here, and I think of some subset of the integers with positive density or positive upper density, then to have an arithmetic progression in here means that if I shift, there's some m, if I shift, there's some point here, and if I shift it by m, it sits in the set. I shift it by 2m, it's again in the set, and again, L times. So so on the face of it, there's certainly an analogy between this and that, but it turns out to be more than an analogy. The two statements are equivalent. So one proves, if one can prove this, then the Summarady theorem follows, and so that's the ergodic approach to it. Now the idea is that the point, I should say, make it more explicit, given the situation which exists in the Summarady theorem, in other words, the set E, I can attach to it a system, and there is a measure-preserving system, and a set A with positive measure, such that you have this result, and this result corresponds to, well, a little bit more than just there exists some arithmetic progression. It means that there exists lots of arithmetic progressions. Now, so we can attach to a subset of the integers a measure-preserving system, and part of the idea of that is that the shift. We're talking here about shifting. I can shift the point, but I can also shift the set. And then what we're saying, if we shift the set in this way, then we have a non-empty intersection. So the shift is something like a measure-preserving transformation. And the important idea is that given the setup in the integers, there is a measure-preserving transformation which corresponds to it. Now, this makes it quite natural to go on to amenable groups, because the property of amenable groups is that just like you have a notion of density here, well, upper density, there's a similar notion for any amenable group. Now, an amenable group can be characterized by the fact that there is a notion of long intervals. As you recall, we defined positive upper density by looking at long intervals, arbitrarily long intervals. Now you have something like that for an amenable group, something called a Felner sequence, and these are sets. They're in an arbitrary group. Usually, in this formulation, you would use a discrete group. Given an arbitrary group G, basically a sequence of sets. I write F for Felner. This is a Felner sequence if for every element in the group, shifting the set by that element makes less and less of a difference the further on you are in this sequence. Just like intervals. The longer the intervals are, if you shift it by one, it makes hardly any difference. So for all G, the number of elements in Fn, if the number of elements in GFn intersect Fn divided by the length, the size of Fn, that this goes to 1. Or that the discrepancy goes to 0. So this characterizes an amenable group. And in an amenable group, it turns out that every subset of the group can be assigned some notion of density. Not uniquely, but it'll be some notion of density by taking some sort of a limit of this kind of expression. So if I have a subset E of the group, I look at the limit. Actually, I look at the limb sup to get the upper density, positive upper density limb sup of the set E intersect Fn divided by Fn, the proportion of the set that's in this Felner set. If this is bigger than 0, then I say that E belongs to positive upper density for the amenable group. And so again, it's not quite trivial, because what one uses in improving the ergodic version, one uses a certain structure theorem for measure-preserving transformations, and it's not that easy to go over to amenable groups. At any rate, there is this paper which just recently came out on the archive, and haven't really checked all the details. At any rate, that tells you that the theorem is also true for amenable groups. There's another kind of result which you could say belongs to Ramsey theory, and which makes sense for arbitrary groups. we say that a set. So we have the notion of positive upper density. We say that a set is thick. E contained in the group is thick if for any finite set F, this time F for finite, there exists a G such that GF is contained in the set E. In other words, E translates of any kind of a finite pattern in the group. It can be moved into the set. And it's actually obvious. So it's obvious not only for a thick set, which will have, first of all, a thick set in the integers not only has positive upper density, it has density 1 or upper density 1, because in an interval you can push any finite set, and actually similarly for an amenable group, if you look at these, if something is thick, then it has this, and such a set has this property, and but the theorem is a theorem by Bergelsen and myself. It involves another notion that if G is minimally almost periodic, which I'll define in a minute, and G amenable, and E is a subset of positive upper density, then it's not necessarily true that E is thick. You can give counterexamples easily, but what is true is that then E times E inverse is thick. Now, first of all, what does minimally almost periodic mean? If G has no finite dimensional representations, or equivalently, and that's more in keeping with the notion of almost periodic. It has no homomorphism to a compact group. Something has homomorphism to a compact group, then by Peter Weil, it has finite dimensional representation. And conversely, if it has, then it certainly has compact homomorphisms to a compact group. So this is a kind of necessary condition for this property to have this property, and here amenability comes in. And that's a good question. It's a good question. I was trying to think of it. I don't know offhand. Somebody here must know the answer to that. I hope there are examples of that. I think maybe the union direct sum of simple groups would have that, is amenable. A finite direct sum of finite simple groups is amenable, and it is minimally almost periodic because it can't have, because of the simplicity, it can't have such maps. Okay.
Any finitely generated simple group. It should be amenable.
No, but I need amenability. Our problem is to try to generalize these two phenomena to non-amenable groups. And there the idea is something that has been developed to a great extent by Elie Glasner as well as myself. You have the notion of instead of a measure-preserving system, there's a notion of a stationary system. what is a stationary system? It's a system where you don't have a, you may not, what I should say about an amenable group, a characterization of an amenable group, one characterization which is not hard to see is equivalent. If G amenable and G acts on a compact space, okay, let's call the space X, then there exists an invariant measure under the whole group on X. There exists a mu belonging to the probability measures on X, invariant and defined on Borel sets, such that mu is invariant under the group. And this is, in fact, I didn't mention it, perhaps I should have mentioned it, that this is the reason that you can use the ideas of the Gadik-Samorady theorem for amenable groups, because you have such an action which is measure preserving, and you can talk about notions of recurrence and so on for an amenable group. Now, what about a non-amenable group? This is actually a characterization of G is amenable if and only if it has this property. And so a non-amenable group does not have this property. It may not have an invariant measure, but what it always will have is something called a stationary measure. Now, a stationary measure is relative to some measure, some probability measure on the group. And in some sense, stationary will mean that on the average, if I shift by elements of the group, on the average, the measure is invariant. Well, I'll write that down explicitly, but more explicitly, so let's see for example, say on the free group on two generators. So there you can look at the measure which assigns measure 1/4 to say A and B are the generators, assigns measure 1/4 to the element, the word or the letter A, B, A inverse, and B inverse. That's a probability measure. And we would say that a measure on a space on which the free group acts is stationary if the average under the action of each of these four elements gives you the same value as the measure. Well, more explicitly, a stationary system or a stationary G system, well, let me write G mu system, is a space, is a XB probability space as before, with, for any set B, Borel set, any Borel set B, the measure of B is the average of the measure of G inverse B averaged over these elements G on which the measure mu sits. I'm sorry, yeah. Oh, right, a G mu system is an XB nu. Right, I'm sorry. And the measure nu of B, yeah, is the average of what the terms would be, averaged according to the measure mu. And now what turns out is that more or less on any group, or certainly on any, basically we, on locally compact, sigma compact group G, with a probability measure mu, in principle an arbitrary probability measure mu on the group, we can find not an invariant density as we can for an amenable group, but we can find a stationary density. What would a stationary density be? It would be, you would have a similar, let's call the density that corresponds to mu, let's call it mu hat of a set E in the group, would be, instead of the same as, this isn't invariant, it's not the same as mu tilde of the set shifted, but the average of these, the integral of mu nu tilde. I'm sorry, right. Well, let me write it as nu tilde. No, I guess it would be mu tilde of E is the average of the measure, this density of G inverse E integrated by d mu of G. No, and this is now density. This is going to be defined for arbitrary sets in the group. And the point is that once you fix the mu and you've also fixed this this density which satisfies this, then you again have a correspondence principle. Again, there'll be a stationary action for which this holds, and where you can correspond sets in the group to sets on the space. And so the corresponding Samarati theorem will tell you which will be valid, and that's basically a result of Glasner and myself, that well, again, because you can prove the ergodic theoretic setup, and again, so given the set E inside G with positive, with this mu tilde, and I haven't said what the mu tilde is. So let me give a possible definition. There will be more. There may be many definitions of an invariant of a stationary density, but one way of getting a stationary density is to simply define mu tilde of a set E to be a limit, some limit of 1 over n, and here we write down mu of E plus mu star mu of E, that's the convolution, plus etc., plus mu star mu n times of E. And you take the limit of this, and now what is the star? The convolution of two measures, mu1 star mu2 of a set of a set. Well, it's in a way easier to write what is meant if I integrate a function f with respect to the convolution of d, I should say, d of mu1 convolved with mu2 of g. So this is by definition. You can say f of g1, double integral f of g1 g2 d mu1 of g, g1 d mu2 of g2. In other words, it's the distribution. If we take the product of two elements, one given the distribution mu1, the other distribution mu2, then this is the distribution of the product. You can also define it for sets. At any rate, you have this notion of convolution, and then you take the average of all of these, and it's pretty clear that if I were to convolve this again with mu, then I get more or less the same thing. It only differs at two points, and after all, I'm dividing by n. So it is possible for any good group to define such a stationary measure given the measure mu. And these are ordinary measures. It's the ordinary measure of E, where mu is some finite measure. And so here the correspondence theorem is that so again you have this correspondence that if E belongs to this general group, for example, the free group, and I'll give an example. I'll say how you can compute this mu tilde, an example of a mu tilde on the free group. If E belongs to G with the measure mu tilde of E positive, then there exists a stationary system xb nu, with nu a stationary measure which can also be written as mu star nu equals nu. As soon as you have a product defined, if you have a product of two spaces, for example, G cross X into X, which is defined because X is a G space, then the convolution is defined, and stationary means this statement. So there exists a stationary system with respect to mu, with respect to measure mu, and a set A with measure nu of A positive, A belonging to X, nu of A positive, and any combination of so it'll turn out that the mu tilde of, if you take any G1A intersect G2A, nu of this, GKA, any expression of this type will be the same, is less than or equal to the mu tilde of the same kind of expression with regard to E. So you have this correspondence where one reflects what's happening on the measure space, reflects what's happening in the group. So if you know that this is positive, then in particular this will be non-empty. So the theorem, there are two theorems now which can be proved. One is fairly general and the other is rather special and represents, we might say, work in progress. So in general, let's hold this theorem A. Here this needs, I need another definition. A group G is order unbounded if there exist elements G n belonging to G of order n for arbitrarily large n. Order of Gn. Now there's the first power that gives you the identity, order of Gn, either infinite or at least n, arbitrarily large n. Now, by the way, if a group has a cyclic subgroup, which many groups do, then something like an analog of the Bandar theorem is not interesting, because any coloring of the group is also coloring of the subgroup, and if you have a geometric progression there, then you already have it in the group. At any rate, the theorem in general is that if for a fairly general group, this is the one requirement. So if G is OU, point is that if a group has if every element has order 7, then you're not going to find a bona fide arithmetic progression of length 8. If G is order unbounded and E is contained in G with mu tilde of E positive, then E contains arbitrarily long geometric progressions. In the other direction, in connection with the theorem about thick sets, this is, I would like to know it in general, and all I can prove, and even this I haven't written down completely the details, let's call this theorem B, for G equals SL2R. and E contained in G. Well, there exists. So first of all, there exists a mu in G. Basically, it'll be a rotation, more or less any rotation invariant measure on G, such that that if mu tilde of E is positive, then E inverse is thick. Now well, again, in the first case, what one does is to get this. In both cases, one finds a stationary system which reflects what's going on in the group, and so in the first case, you have to find for theorem A, you have this stationary system, and you want to show that given a set of positive measure in the stationary system, there exists, so we have stationary, let's say again, X nu stationary for G mu. Then there exists an A, and nu of A is positive. Then there exists for any finite number, there exists a geometric progression that will correspond to the statement that there exists a G with A intersect G, GA intersect G squared A, and so on, intersect G to the LA, that this has positive measure. For the other theorem, what one wants to show, this is for theorem A. For theorem B, what one wants to show is that you look at the stationary system for G mu, and what you want to show is that, and again you have A corresponding to, the subset A corresponds to the set E, and what you want to show is that for any finite number of elements, for any, say, gamma 1 up to gamma k in the group, there exists some G, that is to push this finite configuration into the set E, and for that what you want to do is to get a G such that GA, and again we take A having positive measure, new measure, so there exists a G such that GA intersects each of these sets gamma I A. And you can see how that relates to the original, to the other statement, because this will mean that G inverse gamma I takes A into A. Now this takes A into A. Now this intersects A, and that will mean that this will imply that G inverse gamma I of E intersects E, and this says that gamma I E. Well, now let's bring this to this side. This is non-empty, and this says that GE intersects each of the gamma I E's, and therefore, or that gamma I belongs to GE E inverse, or what I need really is that G inverse of gamma I belongs to E inverse. Again, that I can push all the gamma i's into this set, which means that the set E inverse is thick. Now the key to all of these results is a structure theorem for stationary systems. And to formulate the structure theorem, we need the notion of a strongly proximal system, a strongly proximal stationary system. So we have the system X, and let's write it nu, and the idea is that that we can squeeze this measure nu onto well, actually strongly proximal is just a strongly proximal system. Well, actually we need stationary system here. It means that that typically a typical sequence Gn will map this measure, will squeeze this measure to a point measure, to some delta z, a point measure in X. It has a strong squeezing property. This relates to the notion of Poisson boundary, because a Poisson boundary is in some sense the largest space in which a group can have this action. And what's special about the SL2 is that we know exactly what its Poisson space is for more or less for any measure. Certainly for certain measures, if we can choose the measure, then SL2, if I think of it as Möbius transformations of the disk, the Poisson boundary of this maximal strongly proximal space will be the circle with Lebesgue measure on it, and so we recognize that directly, and then we can use that in the structure theorem, which I'll formulate. We then have the notion of a standard system. It's a system that's built in two stages. Here this will be X, and I write it this way because there'll be a factor system, an image system, Y, with the measure here going into measure down here, let's say theta, where the action here is going to be strongly proximal. So here it has a squeezing property. And the opposite of strongly proximal is measure preserving, that you never change the measure, so they obviously can't squeeze it to a point. And so here what you have is relatively measure preserving. So if you look at the fibers here, any measure nu on this space decomposes into fiber measures, and the way the group acts is it takes each of these fibers into the corresponding fiber and preserves the measure. This is relatively measure preserving. And when you have this, we call it a standard system. Now, the main structure theorem tells you that every system has an extension to a standard system. Now, if you want to prove a theorem about a system, it's enough to prove it for an extension. So it's enough to prove this theorem about, say, this either B or A for a standard system. It turns out that A is not that hard to show, that you use the fact that it's quite easy to see that on Y you can get this kind of intersection property, and then you use that and the fact that here it's measure preserving, using the ordinary Samarati theorem, the combinatorial theorem. Using that, you show that you have this this intersection which you need up here. Here you have the set A, and you look at what's happening here. The B is a little bit harder to show, but again, it can be shown. I know how to show it more or less for this particular group. I suspect that it's true much more generally. Just for the free group, let me just refer to theorem A for the free group. Since you have this condition for positive measure, if I take the measure mu of delta A or delta B or delta A inverse, etc., equal to 1/4, then the notion of a density for mu tilde you're averaging over the different convolutions. The convolutions spread out over words of bigger and bigger words, and so the thing will have positive density with respect to the mu tilde if for every length bigger than some length of the words of that length, your set occupies a proportion delta, at least delta. That would be an example of a set of positive stationary density, and for that you have the Samarati kind of theorem, and it would be nice to know that you also have this other theorem about thick sets. Okay, thank you.